About 100 years ago, we discovered that the source of light and heat in the universe, the most common energy source in the entire world, is fusion. What we're trying to do here is we take a giant donut-shaped vessel and we inject it with just a few grams of two forms of hydrogen, deuterium, which has an extra neutron, and tritium, which has two extra neutrons, into this gigantic 800 cubic meter donut. And then we run electricity through it. When you run electricity through certain gases, you split the electrons from the nuclei, so you have a charged plasma. Because charged particles are subject to magnets. So we put magnets out around, we put magnets sort of this way around the donut, and we put a big magnet in the middle. So we have created now a plasma inside the steel cage, an invisible magnetic cage that can hold these particles in place. Now we're going to heat it, and we're going to heat it to about 10 times the temperature of the sun. No material on Earth can withstand that, 150 million degrees. No material can do that. So the cage, the steel cage, is bounded by this invisible magnetic cage. And through doing that, we get to a point where so many fusion reactions occur that we're getting, our goal at ITER is to get about 10 times the energy out of the plasma that we put in as heating into the plasma. So that's really the goal of ITER. We call that a burning plasma, a self-heating plasma. Remember we said deuterium, tritium going in. What comes out is a helium nucleus and a neutron. The neutron is the only uncharged particle, which is very cool because that will escape the magnetic field and it will hit the steel wall, the magnetic metal wall of the tokamak, of this donut. And in hitting that wall, it's just like if you shot a bullet into a steel plate. The kinetic energy, if you felt the plate afterward, it would be hot. The kinetic energy turns to heat. And the goal is to extract that heat, which not at ITER, but in commercial machines, would produce electricity.